Welcome to the first part of the module on concurrency motivations and challenges. In this part, we explore key motivations for developing concurrent mobile device software. These days, a prime reason for using concurrency is to leverage advances in hardware and software. Multi-core processors are becoming ubiquitous, to the point where it's getting hard to buy a computing device that just has one core. This link describes a wide range of quad-core Android phones. Operating systems like Unix, Windows, and VxWorks are optimized to exploit these multiple cores efficiently via threads, which are the smallest sequence of programming instructions that can be managed independently by an operating system scheduler, as described at this link. Likewise, middleware, such as Java virtual machines, web servers, Android, .NET, DDS, and Corba, can take advantage of multiple cores, as described at this link. Knowledge of concurrency is therefore necessary to program multi-thread and multi-core systems effectively and improve various software quality attributes, such as simplifying program structures to avoid overly complex and tangled event-driven software architectures, increasing performance by overlapping communication and computation to run in parallel, and improving responsiveness by processing user interface operations in a different thread than other background processing operations. The rest of this video explores each of these motivations in more detail. Hardware and software advances can help improve the way programs are structured to avoid overly complex and tangled event-driven software architectures. Historically, the GUIs in early versions of Windows, Mac OS, and Unix were structured using an event-driven programming model, where a single event loop processed user interface events and initiated file and network I/O operations in one thread of control. This link provides more information on event-driven programming. Programming purely event-driven software is hard, however, since the structure of its control flow is obscured in both time and space. In particular, any time a program might block, such as when it performed a read operation on a network connection, it had to post an event on a message queue and handle the operation later in its event loop, which was awkward to program and hard to optimize. This link describes the pros and cons of a pattern called the reactor that's common in event-driven programs. Now that modern middleware, operating systems, and hardware have better concurrency support, more effective ways of structuring application and system software have emerged based on multi-threading, which enables blocking operations that detangle event-driven programs, as described at this link. For example, Android provides several concurrency frameworks that enable multiple threads to perform long-running computations in the background, which maps efficiently onto multiple cores. Moreover, these background computations can block independently of each other and the user interface thread, which allows developers to structure their software more cohesively. Using these Android frameworks effectively requires knowledge of concurrency patterns, which are described in this link. To illustrate one common Android concurrency model that uses so-called worker threads, here's a snippet of code from an application we'll explore throughout this MOOC that enables a user to download an image from a remote server across the network. The structure of this code is based on the half-sync, half-async pattern described at this link and covered later in this section. This example has a click listener that handles buttons pressed on the Android touchscreen. When a user presses the download button, this code starts a worker thread that runs in the background and blocks while downloading an image. After the image is downloaded and processed, it's displayed via the user interface thread. If you look carefully at this code snippet, you'll see how concisely structured it is. In particular, the image download and display logic is cohesive in time and space, rather than being scattered throughout the code, as would be the case in a purely event-driven solution. This link describes the Android worker threads concurrency model, which we'll cover later in this section. Hardware and software advances also allow developers to increase application and system performance, which is a key motivation for using concurrency. In particular, performance can be accelerated via parallelism, as described in this link. Android accelerates performance via parallelism in several ways. One way is to overlap computation and communication operations via its multi-threading mechanisms. For example, in the image downloading application we examined earlier, the background threads that download images can run in parallel with each other and with a thread that interacts with the user. This link provides more information on Android multi-threading mechanisms. Another way to accelerate performance on Android is to use the render script framework, which parallelizes work across all processors available on a device, such as multi-core CPUs, GPUs, or DSPs. RenderScript is targeted at applications performing image processing, computational photography, or computer vision, as described in this link. Despite advances in hardware, not every computing platform in use today supports multiple cores. For example, you may have an older device with just one core, or there may be other constraints that make it hard to take full advantage of parallelism. Concurrency can still be useful, however, to improve perceived response time, such as ensuring the user interface doesn't ignore input from users while other operations are being processed. For example, the Android user interface thread can interact responsively to user gestures and other input, while worker threads can currently execute long-running computations in the background and perform blocking operations on the file system and network. This link provides more information on responsiveness in computing systems. In summary, there are several motivations for developing concurrent software for mobile devices. It helps developers effectively leverage technology advances, such as Moore's Law and other means by which commoditized hardware and software gets better, faster, and cheaper at a regular pace. Concurrency also helps developers meet the quality and performance needs of their applications and services by going beyond what's provided by lower-level infrastructure, software, and hardware. For example, Concurrency allows developers to structure their software so it's more responsive to user interaction patterns, as well as easier to understand and evolve over the software lifecycle.